Good evening, everybody. My name is Chatzis, undergraduate at the University of Crete, and today I will convince you why strongly magnetized neutron star X-ray binaries are something you need to know about in your life without even realizing it. So, let's talk about some stuff, shall we? To start off, let's begin with a side-by-side comparison of the two most common categorizations of X-ray binaries, namely low and high mass systems. In the former, we have a black hole or a neutron star, weakly magnetized with a strength of approximately 10 to the 8th or 9th, while in the latter, the magnetic field reaches values of 10 to the 12th. High mass systems have also a disk that stops far away from the innermost stable circular orbit, unlike low mass systems. Another distinction also lays in the fact that while low mass X-ray binaries transfer mass through Roche lobe overflow, their counterparts form accretion columns. And it is from those accretion columns that high mass systems emit X-ray radiation, whereas X-rays in low mass systems stem from the disk and or the jet. However, since we can also have radio emission from the jet, something interesting happens there. We can derive a radio X-ray coupling, as it apparent here through a plethora of data. Here, blue data points represent black holes and green neutron stars. The red ones are black holes or black hole outliers that don't follow the standard correlation. The colored planes illustrate beautifully the coupling and also note the respective slopes. Please note and keep in mind for later that the data points stop about 10 to the 37th. We are below the Eddington limit here. The aforementioned high mass systems are not so keen though on sharing any radio emission, although it is not uncommon to have gamma ray or radio emission from an isolated neutron stars or young high mass X-ray binaries with large orbital periods. Accretion and radio emission were always thought to be irreconcilable. And that begs some questions. Could such conditions exist where a radio bright jet would form in such accreting systems? Would there be an ultra-fast outflow? And even if these conditions could be met, would there still be a correlation between X-rays and radio, similar to the not-so-shy radio-loud low-mass systems? Those are some 1 million questions right there. And why not ask the audience? Science should be, after all, based on exchange of ideas. So please feel free to share your knowledge after the presentations. However, the general consensus says no. We do not expect radio from systems like these. Is this notion true, though? Well, you could argue that for me to ask this question, the answer would be no. And indeed, you would be right. Thought to not exist, yet measured. During an X-ray outburst of this system over here, which name I will not pronounce, we got the first radio detections of a high mass X-ray binary. Those observations have been taken through eight epochs and 2 months, from October 2017 to January the following year. And what is especially fascinating here is the fact that not only do we have a nice correlation between radio and X-rays, as you can see, but this also happens above the Eddington limit. Unlike the low mass X-ray binary data, I ask you to take a mental note of. This system, however, does not stop to surprise us. From February through May 2018, we got 7 more epochs. And the most intriguing aspect of the second wave of observation lays in the fact that although X-ray fell well below the Eddington limit, the radio detections were as bright as before. And as one can easily see now, there isn't any correlation between radio and X-ray emission, since in the first wave of observations. Van den Eyden argues in favor of re-examining our understanding of jets and systems with strong magnetic fields, believing that the observations can be explained by implementing a jet. We, on the other hand, examine the possibility of non-thermal emission from a shock stellar outflow. But before going into further detail, let's take a closer look at this truly exotic system. Right. Gaia observations reveal that it has a minimum distance of 5 kiloparsec to us, with a median of 7.3 kiloparsecs. with an orbital period of 27.7 days, one can arrive that the binary separation distance is 7.37 times 10 to the 12 centimeters. In this picture over here, we also can see how the system fits in with the low mass counterparts. Please note, however, that the low mass data has been converted from 5 gigahertz to 6, assuming a flat spectrum, so as to be on par with the Swift data. Also, through Doppler shifted absorption lines, we moreover know that there is a fast outflow, which only further compels us to examine the possibility of a colliding the outflow colliding with a VE wind, thus creating conditions for non-thermal radiation. So let's expand on this idea, beginning with our main assumptions. Basically, everything has spherical symmetry here. We truly embrace the spherical cow analogy. And if it isn't a sphere, it most probably is a line. Therefore, we have a spherical symmetrical BE wind instead of more common equatorial winds. And we basically also ignore the existence of the neutron star disk. And although called a bow shock, technically for us, a circle shock would be more appropriate of a name. In our analysis, we also do not concern ourselves with effects of orbital motion. The mass transfer from the companion star to the neutron star happens somehow. It does not interfere with a shock, but we do not consider anything like this. Since the shock can happen rather close to the VE star, we assume that in order for the wind to reach its terminal velocity, the shock must happen at a distance no less than twice the radius of a star. All right. Let's talk now a bit more about our geometry and our core equations. Right. In order to determine around which object the shock is bent, we use the wind momentum ratio, consisting of the mass loss rates and the terminal velocities of both the neutron star and its companion. If eta is smaller than 1, the shock is around the BE star, while eta greater than 1 signals a bend around the neutron star. After the shock, we can determine the energy density of the BE wind through exactly those parameters here. The D is the binary separation distance, as before. And we can also see here that the distance to the contact discontinuity from each object. Assuming equipartition, half of the energy goes to the magnetic field, and the other half to the electrons that have been accelerated into a power law from a minimum to a maximum Lorentz factor, with a minimum being a free parameter. Now, we can calculate the non-thermal emission, while also accounting for the free absorption and the thermal Bremsstrahlung of the wind. So, let's take some time to see where this leads us. Starting with some radio spectra. Going from left to right through the plots, we can see that we change the X-ray luminosity, while going from top to bottom, we see that the free parameter gamma min changes. Each plot consists of 3 different wind models. The first 2 share the same terminal wind velocity, while the last one shares the same mass outflow rate with the first. The dashed lines here represent the Bremsstrahlung of the BE wind and have been added to the total spectrum. Please note that the star model with an outflow of 10 to the minus 7 solar masses per year, this color over here, is independent of, is completely dominated by the Bremsstrahlung in each scenario, right? So we will go back to that in a minute. We can also observe that there appears to be a substantial difference between the spectra depending on our choice of gamma min. So let's understand why by looking at the spectral decomposition. Perfect. The picture has already become a lot clearer. On the right, we have full spectra similar to those before, while on the left, we can see each segment on its own. And the first thing we can notice is that the blue curve in the lower panel has one more segment than its upstairs neighbor. But before we look at the differences, let's focus first on the similarities. In both cases, we have a red dashed line for the BE wind and a black dotted line for the free absorption. The blue line has also two common segments, namely the optically thin part over here and steepened by 1/2 factor over here. This happens for cases where gamma is over a critical frequency, a critical loss factor. Now, if our chosen gamma min is smaller than the characteristic synchrotron self-absorption frequency, we have the optically thick part with a slope of 2.5. If, on the other hand, it is not, the segment splits into two, for cases between those two values and for cases below gamma min. Now that we understand a little bit better the spectra, let's move on to light curves comparing some radio and X-ray luminosity. Again, the same three wind models we had with the spectrum, with the same gamma min distinction. Since those curves are at 6 gigahertz, we can observe something remarkable. This curve over here is completely independent of the X-ray luminosity, which is exactly what I prompted you to take a mental note of. Now, the dashed line signals non-physical scenarios where the shock happens at a distance closer than 2 stellar radii. Recall our main assumptions. And we can also make a break in the slope over here, and also here and here. This basically tells us that the shock changes around which object it is bent. Thus, we have a shock around the neutron star at lower luminosities, while at higher luminosities, as it is expected, the shock is bent around the companion star. However, gamma min is not the only free parameter. They can have a significant change on the shape of the light curves. So why not take a look at 5 more? In the upper row, going from left to right, we start with the slope of our power law that electrons have been accelerated into. In the middle, we have gamma min, which I've already briefly discussed. And we end with a parameter He, which is a number between 1 and 3 that we multiply the neutron star outflow with to account for an accelerating outflow. Right. In the lower row, we start with a parameter expressing how much of the accreting mass is lost as outflow, while the parameter epsilon indicates how efficiently the accreted mass can be converted into energy. Lastly, we also have the binary separation distance as the low right corner. Now, let's take a closer look at plots C and D, for example. In plot C, by increasing He, we increase the velocity of the neutron star outflow, inadvertently creating a stronger shock, or in other words, changing the wind momentum ratio in favor of the neutron star. So as it should be expected, the whole curve shifts a bit to the left. Something similar happens in plot D. By increasing the outflow rate from the neutron star, we again change the wind momentum ratio in favor of the neutron star, shifting the light curves also again to the left. If you're curious about the other parameters, feel free to ask me later. But for now, let's explore some practical usage we can get from all this. Right. We can indeed find parameters that explain rather well the low X-ray observational data for both 6 and 22 gigahertz of the Swift data. Now, you may ask, what about the data at the super Eddington luminosities? Can we do the same there? And you'd be right to wonder. Unfortunately, the way in which we would need to change our parameters are rather non-physical. They don't make really sense. For example, we would need to assume a slower neutron outflow, which one could argue is rather counterintuitive. But enough with the negativity, let's finish strong with something exciting. Now that we discussed the existing data, the newly made observations, and our own model, let's see how all these things fit together. One thing that you may have noticed is that the Swift data basically has its own corner in this plot. The same corner our own model calls home, which is excellent, because this makes it a great idea to expand on and explore further this new territory. If you're really observant here, you might have noticed a small change in the Swift data compared to the previous plot. This is because in this picture, the distance to the system is taken as 5 kilo/sec, whereas in our calculations, we have taken 7.3 kilo/sec. So kudos to you if you managed to see that. Now, so in conclusion, we managed to give a description of radio emission in highly magnetized accreting X-ray binaries, without resorting to the employment of a jet, both in theory as well as when compared to the recent radio detections, as I've showed you. However, open questions still remain. How do we explain this transition from sub to super Eddington without resorting to non-physical changes of the parameters? And how do we explain a fast outflow while below the Eddington limit? There's still work to be done here, which can lead to exciting future research. So thank you for listening.
Thank you very much, Margariti, also for being in time and for this very interesting work. So, yeah, I shouldn't have said that. Okay, please, please, if you have any questions for Margaritis, it's time to ask now. I don't see any hands raised. Okay, not in the chat either.
Okay, great.
Yes, so I could ask one question. You said, Margariti, that we do not consider the orbital motion in our calculations.
Mm-hmm.
So I can imagine that this is rather complicated, but do you have any ideas of how the orbital motion would affect your results?
Okay, let's go back a few slides. It was, here was, right. So let's imagine that we look this from the top view, right? With the orbital motions, when one object rotates around the other in some kind of way, there is, let's say, a tail of mass outflow from the BE star left. So this could, for example, change the results when we calculate absorption factors, for example, the free absorption, because we only take in account the B wind here and not also the trail that is left from this orbital motion. This would be, for example, one way it could change. Also, with this trail, it could also emit somehow, which would also change our observations and maybe add something that we did not account for.
Okay, yes, I see your point. Thank you.